What do we want? Low-flying airplane noises. When do we want them? Meow. That might be corny, but if you got this joke, then you've probably heard of the Doppler effect. To be fair, maybe not everyone has heard low-flying airplane noises, but this is probably how you've heard Doppler effect before. But what exactly is Doppler effect? Well, let's let Sheldon explain.
It's supposed to be. Oh, he's the Doppler effect. Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Okay, I think we're going to need to break that down. So, it's the apparent change in frequency. What that means is you hear a different note. And the relative motion between the source and the observer? Well, in the earlier video, the relative motion was the car drove past the observer. Equally, I could have the observer running past the car and still hear the same change in frequency. In either case, this explains the next video.
So in this video, the speakers are the source and they're stationary. The observer is me taking the video, also stationary. There's no relative motion between the source and the observer, and so all the frequencies sound right. They have the correct apparent frequency. Notice this stays the same in the next video, where the source and the observer are both moving, but they're moving at the same rate. But when the source and observer are moving at different speeds relative to each other, then the frequencies change. Listen really closely as the red truck passes me, the observer. When the car goes towards me, it's like I'm at position Y. The waves get scrunched together, so I hear a higher note. But as soon as the car passes me, it's as if I'm at position X. The car is going away, so the waves get stretched out, and I hear a lower note. Here's a better explanation.
You're like a bird, you're looking right down in the water, and there's a bug sitting there. And this is a lake that's perfectly smooth. But now what the bug starts to do is the bug starts to jiggle up and down. And when that bug jiggles up and down, that bug is a vibration, yeah? And that's vibrating on a nice surface, yeah? We're going to make what? Begin with a W. All right. We're going to make waves, gang. We're going to make waves, okay? And the waves kind of look like this. Where I draw the line, that represents like the crest of a wave, like it might sort of be like this. You kind of see what I'm saying? Okay, so this represents the crest of the waves. And the waves go out in all directions. And the fact that they're circles is kind of evidence that they go out in all directions at the same speed. Isn't that true? Like if it went faster over here, then the wave would sort of be like that, yeah? Okay. So the circles are evidence of the same speed. Okay. Now, what would be the frequency of the waves compared to the frequency of the vibrating bug? In other words, if you put your hand here, blip, 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 the waves would hit your hand, yeah? Certain frequency. How would that blip, blip, blip compared to the whoop, whoop, whoop of the bug? Same. Isn't that right? The frequency of a wave is the same as the frequency of the vibrating source. Makes sense, doesn't it? Let's suppose now that the bug swims in this direction. What the bug is going to do is the bug is going to swim in the direction of the waves that it's producing, and it continues to vibrate a little bit, yeah? Wouldn't the wave pattern look something like this? Can you kind of be seeing that? In fact, what direction would the bugs be swimming, gang? I mean, you can tell it's going that way, right? Well, the bug might be at rest and the water's going this way. I mean, motion is relative anyway, yeah? Okay, now, if I put my hand over here, would I get a higher speed wave, a lower speed wave, or the same speed wave? Check your neighbor. And make sure you're listening to the question that's being asked. How many people say, hey, the speed of the wave is going to be the same? Yay, that's right. The speed of the wave doesn't change. What does change, gang? How frequently that wave encounters you is different, yeah? So I can get a different frequency. When I put my hand here, higher frequency or lower? Can you see it? Over here. Bloop, 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 bloop. That change in frequency due to motion of the source or the receiver is what we call the, named after a person. Okay, good. It is called, it's a Doppler effect. That's right. The Doppler effect is the change of frequency when something moves toward you, away from you, that sort of thing. The change of frequency due to motion.
So, for today's activity then, after you watch this video, I'd like you to go to physicsaviary.com, open up the Doppler Effect lab, and use it to help answer some of the questions on the homework. For this, you'll be able to change the speed of the wave, the speed of the source, and then measure using the grids that are here, the wavelengths. Oh, but one more kind of cool thing. Did you know that if you have a very fast moving object, a source who's faster than the waves it's producing, you get this rippling cone effect. This is actually a sonic boom. In this case, because the plane is going faster than the speed of sound, it's making a shock wave that goes out in a conical shape. The compressions add together with constructive interference, making pressure that's so high it causes water to condense right out of the air, like a cloud that follows the plane.
All right.
And if you listen closely to this video, you hear two sonic booms. One that corresponds to the sonic boom of the front of the plane, breaking the sound barrier, and then the back of the plane. So, one more time. Two sonic booms. And we'll talk about this more next unit, but we know that all wave properties are common to all waves. So, if it does it with sound, Doppler effect must also do the same thing with light, causing light from distant stars to be slightly shifted. Our star puts out light that looks like this. One that's moving away from us would have light that's slightly redshifted, and a star that's moving towards us would have the same exact colors, but their dark stripes would be slightly blue shifted. That's all, folks. Best of luck on the lab and homework that goes with it. Have a great night.